Hello dear friends. Now today we will see a new topic, that is stress and strain curve. Now what is this stress and strain curve and what it gives as an information? So the relation between the stress and strain for a given material under tensile stress can be found experimentally. In a standard test of tensile properties, a test cylinder or a wire is stretched by an applied force. The fractional change in length, that is the strain, and the applied force needed to cause the strain are recorded. The applied force is gradually increased in steps and the change in length is noted. A graph is plotted between the stress, which is equal in magnitude to the applied force per unit area, and the strain produced. We can find a typical graph for this metal is shown in this above graph or a figure. That analogous graph for compression and shear stress may also be obtained. The stress strain curves vary from material to material. These curves helps us to understand how a given material deform with increasing loads. From the graph, we can see that in the region between O to A, the curve is linear. So here we can find that between O to A, from origin to point A, it is a linear. The curve is linear, and in this region Hooke's law is obeyed. Now the body regains its original dimensions when the applied force is removed. In this region the solid behave as an elastic body. So initially when we studied that the elastic nature is the nature when some deform is produced due to external force, but when that force is removed, the force is released, the object regain its original position. That type of material are known as elastic material, and here it will behave as elastic nature. Now in the region A to B, here we can find different regions as per as our concern. So first region was O to A. Now the second region is from A to B. Here we find some curveness. So here we say that in the region from A to B, stress and strain are not proportional. The body still returns to its original dimension when the load is removed. But this time it will not trace the same path. The point B in the curve is known as yield point, or it is also known as elastic limit. And the corresponding stress is also called yield strength of the material. So here initially the condition OA in which object behave as 100% elastic material, but now when it reaches to B, it is converted to the limit of elasticity, or it is also called elastic limit. So that means after point B, the material will lose its nature of elasticity. Up to A, it is almost 100% elastic. Now up to B, still it is elastic, but at point B, its elastic limit completes. So at B, it is called elastic limit. Now if the load is increased further, the stress developed exceeds the yield strength and strain increases rapidly even for a small change in the stress. The portion of the curve between B and D shows this condition. So in B to D, all these condition we can find three different things. See, here at point B, we found the yielding condition. So here this condition can be explained as a sigma y. But when more stress or external force is applied, we can simply say that the portion of curve between B and D is shows that the small change in an external force, the strain increases rapidly and it gives the nature as shown in the graph from B to D. Now in between that there is a region that is B to C and the point C, where we can say that up to that point some permanent set is developed. Now we will see that what is that permanent set. So when the load is removed, say some point C between B and D, the body does not regain its original dimension. Now in this case, even when the stress is zero, the strain is not zero. The material is said to have permanent set. So here in this region, I have shown with that arrow, here some permanent set is established. So permanent set is established and this deformation is said to be plastic deformation. Now the point D on the graph is the ultimate tensile strength. So here we can say that this point D is the maximum limit of that ultimate tensile strength, which is also explained by sigma u. Now the point D on the graph is the ultimate tensile strength of the material. Beyond this point, additional strain is produced even by a reduced applied force and the fracture occurs at point E. So this point E is called fracture point. Here we can say that at this point it is called a fracture point. Now if the ultimate strength and the fracture points D and E are close, the material is said to be brittle. So if these D and E are very close to each other, they are called brittle. If they are far apart, the material is said to be ductile. So here we can find out by the graph that whether the material is brittle or ductile. If the distance between this D and E is small or close to each other, it is called brittle material. But if the distance between D and E is more, it is called ductile material. So this is one type of graph that is shown and explained. Now another type of graph is also observed for stress and strain. So we will discuss that graph also. Here it is also called that hysteresis, and here I would like to explain it also. In this case, the stress and strain are having totally different nature. Here again stress of very big amount. So about, that is about 10 to the power 6 Newton per meter square, and the strain is also comparatively high. So we can say that here strain is also comparatively high. If we draw a graph for a particular type of material, it will be like this. So now we will try to understand what this graph means. Here we can say 0.5, here we can say that 1.0, here again in the same manner it is 0.5, and here we can say that it is 1.0. So now we will see that what this graph shows. This graph is of stress versus strain curve for elastic tissues of aorta, the large tube or vessels carrying blood from the heart. So if any material shows this type of nature between stress and strain, then how to understand them? For that, we can explain that, as stated earlier, the stress strain behavior varies from material to material. For example, a rubber can be pulled to several times its original length and still returns to its original shape. Now in given figure 2, it shows a stress versus strain curve for the elastic tissue of aorta, which is present in heart. We have to note that although elastic region is very large, the material does not obey Hooke's law over most of the region. Now secondly, there is no well-defined plastic region in this graph also. Substances like tissue of aorta, rubber, etc., which can be stretched to cause a large strains, they are called elastomers. So the second graph belongs to the material called as elastomers. So this is the case how the stress and strain curve can be explained. Now the next that we will study, that is elastic moduli. So we will here discuss that what the elastic moduli is. To understand this elastic moduli, we can put the term that what the elastic moduli is. So here we will discuss about it, that what is the elastic moduli is. So we will try to understand the phenomena again, that what this term means. So the proportional region within the elastic limit, the stress and strain curve, which is the region of O to A in this above graph number 1. Here if we go with this graph 1, the proportional region within the elastic limit, the stress versus strain curve here in the region OA, of a great importance of the structural and manufacturing engineering design. The ratio, that is stress and strain, is called modulus of elasticity and found to be characteristics of the material. So that is called that modulus of elasticity, and that ratio, that is sigma over E, is termed as modulus of elasticity. So Here there is a new term, that is modulus of elasticity, and the term modulus of elasticity is equals to, that is sigma over epsilon, that is stress versus strain. Out of all these things, first of all we will try and understand Young's modulus. This is very important topic and we will discuss that Young's modulus. So we will see that what is this Young modulus is and how it defined for different type of materials. So the experimental observation shows that for a given material, the magnitude of the strain produced is same whether the stress is tensile or compressive. The ratio of tensile or compressive stress to the longitudinal strain is defined as Young's modulus and is denoted by the symbol capital Y. So Young modulus is given a symbol capital Y and it is equals to sigma over epsilon. Now we have very well known equation, that is sigma is nothing but force over area. So here we can say that this sigma is force upon area, and at the same time epsilon is the change in a length over original length. So when we apply this equation to our knowledge, we can find that F over A, now the denominator of denominator goes to numerator and the term that will be in a denominator will be like this. Now the strain is a dimensionless quantity and therefore the unit of Young's modulus is also the same as that of stress, and that is the unit of Young modulus is Newton meter raised to minus 2. So unit will be Newton meter raised to minus 2. So here it is very well clear from the equation. This unit is also called the unit of pressure, that is Pascal, in the remembrance of a great scientist. Now, from the data that we can find out from the table that is given in textbook on page number 235, we are provided some Young modulus and elastic limit and tensile strength of different materials. So in that materials or from the table, that for the metals the Young's moduli are large and therefore these materials require a large force to produce small change in a length. To increase the length of a thin steel wire of even 0.1 centimeter square cross sectional area by just a 0.1 percentage. So if we want to increase the length of 0.1 centimeter square cross section steel wire by just 0.1%, a force of about 2000 Newton is required. The force required to produce the same strain in aluminum, brass and copper wires having the same cross-sectional area are about 690 newtons, 900 newtons and 1100 newtons respectively. It means that the steel is more elastic than copper, brass and aluminum. It is for the reason that steel is preferred in a heavy duty machines and in a structural designs. Wood, bone, concrete and glass have rather small young moduli. So this is actually the young moduli and the explanation about it.